Ever found yourself thinking about why nothing zips past the speed of light? Well, it's a fascinating topic to dive into. Imagine light travels at a staggering speed of approximately 300,000 kilometers per second. That's fast enough to circle the globe 7.5 times in one blink of an eye. This cosmic speed limit, known as the speed of light, is a constant that plays a critical role in our understanding of the universe. It's intimately linked to space, time, and the very fabric of reality, thanks to a certain Mr. Einstein and his theory of relativity. In fact, as per Einstein's famous equation, E equals mc squared, the closer an object gets to the speed of light, the more its mass increases and the more energy it requires to keep accelerating. So it's not just a matter of speed, but of energy and mass as well. So if you're planning to beat light in a race, you might want to reconsider. So, before we delve into the speed of light, let's understand what speed really is. You see, speed is simply how fast something is moving, or if you want to get a bit technical, it's the distance covered over a specific period of time. So, if you were to run across a football field in 10 minutes, your speed would be the length of the field divided by 10. Now, speed isn't a one-size-fits-all concept. It varies depending on the context. For instance, the speed of sound is a whopping 762 miles per hour. But that's nothing compared to the speed of light, which travels at a jaw-dropping 670 million miles per hour. Here's a fun way to think about it. If you were to race against light, it would zip around the Earth 7.5 times before you could even say go. Now that we've got a grip on speed, let's step into the world of light. Light, it's not just for seeing where your socks disappeared to in the dark. In fact, light is a bit of a show-off. It has a dual personality. It behaves both as a wave and a particle, a phenomenon we call wave-particle duality. Imagine you're at the beach, watching the waves roll in. Now try to picture light behaving in the same way. It undulates through space, just like those ocean waves. This wave-like property allows light to interfere with itself, create diffraction patterns, and display other wave-like phenomena. But wait, there's more. Light also behaves like a particle. This particle aspect is known as a photon, and it's the smallest discrete amount or quantum of light. These photons, like the rebellious teens they are, refuse to be slowed down by anything, not even the densest of media. They always travel at a constant speed in a vacuum, a whopping 299,792,458 meters per second. That's approximately 7.5 times around the Earth in just 1 second. Now you might be wondering, why does light have this dual nature? Well, it's because of our good friend quantum mechanics. This field of science tells us that all particles have a wave nature and vice versa. It's just that for most things the wave nature is too small to notice, but for light, it's just right. The Goldilocks of physics, you might say. So light has its own unique personality, doesn't it? But what keeps it from going faster? Stay tuned as we delve deeper into the intriguing world of light speed in our next scene. Einstein, with his wild hair and insightful mind, had a lot to say about this. Among his many brilliant ideas, one in particular set the stage for our understanding of the speed of light. That idea was his theory of relativity. Now, Einstein's theory of relativity is a bit like a perfectly baked Victoria sponge. It has 2 layers. The first one, the special theory of relativity, states that the laws of physics are the same in all inertial frames. This means that whether you're on a train, speeding down the tracks, or sitting still in a park, the laws of physics work the same way. The second layer, the general theory of relativity, is a bit more complex. It involves gravity, space-time, and the idea that mass can curve space. But let's save that for another video, shall we? Focusing on the first layer, special relativity, one of its key postulates is that the speed of light in a vacuum is always constant, regardless of the motion of the source or the observer. This is a bit mind-boggling, isn't it? It's like saying that no matter how fast you're running, the speed of a thrown ball will always appear the same to you. In our daily lives, we're used to the idea that speeds add up. If you're running at 5 miles per hour and throw a ball at 10 miles per hour to a stationary observer, it would seem as if the ball is moving at 15 miles per hour. But light doesn't play by these rules. According to Einstein, light travels at a speed of approximately 186,000 miles per second, whether you're standing still, moving towards it, or running away from it. This is an astounding concept, but it's been tested and confirmed in countless experiments. So, according to our friend Einstein, Light doesn't care if you're running alongside it or away from it. Its speed remains the same. And that, ladies and gentlemen, is why nothing can quite catch up with light. Now, the million-dollar question, why can't anything be faster? Well, let's delve into the implications of Einstein's theory of relativity, which we just talked about. According to this theory, as something speeds up, its mass increases. Think of it this way. Imagine you're pushing a car. The faster you try to push it, the heavier it feels, right? Well, in the world of physics, this isn't a mere feeling, it's a reality. Now, this increase in mass isn't noticeable at the speeds we're used to in our everyday life. But as we approach the speed of light, it becomes significant. The closer you get to the speed of light, the more your mass increases. This leads to a rather tricky situation. To continue accelerating, you need more energy. But the more you speed up, the more mass you gain and the more energy you need. It's like a dog chasing its tail. But the tail keeps getting longer and longer. So what happens if we tried to reach the speed of light? Well, we'd need an infinite amount of energy. Yes, you heard it right, infinite. The universe would have to empty its entire energy savings account and then some just to get one object to the speed of light. Talk about a high-maintenance relationship. But let's say, for argument's sake, we somehow managed to harness this infinite energy. What then? Well, your mass would also become infinite. You'd be an infinite mass with infinite energy zooming around the universe at the speed of light. It's a fun thought, but it's also impossible according to the laws of physics as we understand them. So, to go faster than light, we'd need more energy than the universe can provide. That's one hefty fuel bill. While we can't beat light in a race, we can certainly marvel at its implications. The speed of light is not just a speed limit, but a cosmic storyteller. It's like a time machine allowing us to peer into the past. When we gaze at a star that's, say, 4,000 light years away, we're not seeing the star as it is now, but as it was 4,000 years ago. The light from that star has been on a 4,000-year journey to reach our eyes. It's like receiving postcards from the past, sent by the universe itself. But it's not just about looking back, it's about understanding our place in the cosmos. The concept of light years gives us a sense of the vastness of space. The nearest star to us, Proxima Centauri, is over 4 light years away. That means even if we could travel at the speed of light, it would take us over 4 years to get there. It's a humbling realization, isn't it? Now let's dip our toes into the realm of the speculative, shall we? Enter wormholes. A concept straight out of science fiction. The idea here is that these are shortcuts through space, a sort of cosmic subway system, if you will. If they exist, and that's a big if, they could potentially allow us to circumvent that pesky light speed limit. But wormholes are purely theoretical at this point, and even if they do exist, they come with their own set of challenges. They are unstable for one and could collapse at any moment, trapping anything inside. So, perhaps it's best to leave wormhole travel to the imaginations of science fiction writers, at least for now. In the end, the speed of light is not just a barrier, but a window. A lens through which we can explore the universe and our place in it. It's a reminder of both our insignificance and our potential. So while we're stuck in the slow lane, light speed gives us a fantastic view of the universe.